welcome to this problem walkthrough. Today, we'll be tackling LeetCode problem number 1553, minimum number of days to eat n oranges. This is an interesting problem that challenges us to minimize the steps needed to eat all the oranges by leveraging different operations. We'll explore intuitive approaches and analyze their efficiency. Let's get started. In this problem, we are tasked with finding the minimum number of days required to eat all the oranges when starting with a given integer n. The number of oranges decreases based on three possible actions. If n is divisible by 3, you can eat 2/3 of the oranges in one day. If n is divisible by 2, you can eat half of the oranges in one day, or you can eat exactly 1 orange per day. The objective is to minimize the total number of days required to reduce the count of oranges to 0. The input is a single integer n, which can range from 1 to 2 billion, and the output is a single integer representing the minimum number of days required. This means we need an efficient strategy to handle both very small and very large values of n. Let's consider the first example where n equals 10. On the first day, we can divide the oranges by 2 since 10 is divisible by 2. This allows us to eat 5 oranges, leaving 5 oranges remaining. On the second day, no divisibility condition applies, so we eat 1 orange, leaving 4. On the third day, we divide by 2 again since 4 is divisible by 2, eating 2 oranges and leaving 2. Finally, on the fourth day, we eat the remaining 2 oranges. In total, it takes 4 days to eat all 10 oranges. This demonstrates how choosing the optimal eating strategy can minimize the number of days. Now, for the second example where n equals 6, we start by dividing by 3 because 6 is divisible by 3. This allows us to eat 4 oranges on the first day, leaving 2 oranges. On the second day, we eat 1 orange, leaving 1. Finally, on the third day, we eat the last orange. This requires a total of 3 days. For a simpler case like n equals 1, it takes only 1 day to eat the single orange since no other actions are possible. These examples highlight how the problem can involve different approaches depending on the number of oranges and their divisibility. The constraints of the problem require us to consider various edge cases. For instance, when n equals 1, the solution is straightforward as it always takes exactly 1 day. However, for very large values of n, such as 2 billion, we must ensure the solution is computationally efficient to avoid exceeding time limits. Additionally, when n is divisible by both 2 and 3, we need to decide the optimal strategy that minimizes the number of days. Finally, there are cases where n is not divisible by either 2 or 3, requiring us to use the third option, eating 1 orange at a time, strategically until one of the divisibility conditions is met. These considerations ensure the solution is both correct and efficient across all inputs. To solve the problem of finding the minimum number of days to eat n oranges, the first approach we could consider is a brute force recursive simulation. The intuition here is straightforward. We simulate the process by trying all possible ways to reduce the number of oranges. These options include subtracting 1, dividing by 2 when divisible, or dividing by 3 when divisible. The goal is to recursively compute the minimum number of days required for each state. A few key observations make this approach appealing initially. For example, when n is divisible by 2 or 3, dividing the number of oranges is far more efficient than subtracting 1 repeatedly. However, the main drawback here is that this method has a large number of overlapping subproblems. Each recursive call explores multiple branches, leading to an exponential time complexity of 3 to the power of n. This makes the approach computationally expensive and impractical for large input sizes, such as n equal to 1 million. To address the inefficiencies of the brute force approach, we can turn to a recursive solution enhanced with memoization, also known as top-down dynamic programming. The key idea is to eliminate redundant computations by storing the results of subproblems in a memoization table. This ensures that each state is computed only once, significantly improving efficiency. For any given n, we only need to compute 3 subproblems: the state after subtracting 1, the state after dividing by 2 if divisible, and the state after dividing by 3 if divisible. By using a dictionary to store the results of these states, we can avoid recomputing them in future recursive calls. The time complexity of this approach is reduced to n, where n is the number of unique states, and the space complexity is also n, due to the memoization table. While this method is much faster than the brute force solution, it still relies on recursion, which could lead to stack overflow for very large inputs. Another promising method is the iterative dynamic programming approach, which builds the solution from the ground up. Instead of relying on recursion, we solve the problem iteratively starting from the base cases. For instance, when n equals 0, no days are needed, so dp 0 is 0. Similarly, when n equals 1, only one day is needed, so dp 1 is 1. The transition function then computes the minimum number of days for each state incrementally based on smaller subproblems. For a given I, the result is determined by taking the minimum of the three possibilities, subtracting 1, dividing by 2 if divisible, or dividing by 3 if divisible. This approach has a time complexity of O(n) and a space complexity of O(n) due to the dp array. While it avoids recursion and is efficient, it may still be slower than more optimized alternatives for very large values of n. An optimized approach combines recursive dynamic programming with greedy choices to minimize state transitions. The idea is to prioritize the most efficient transitions, such as dividing by 2 or 3 when possible, while still using memoization to avoid redundant computations. This method prunes unnecessary computations by focusing only on the most promising paths to reduce n quickly. The time and space complexity of this approach are reduced to O log n, as the number of state transitions is significantly smaller compared to other methods. However, the implementation is slightly more complex than the iterative DP version, as it requires careful handling of the recursive calls and the greedy pruning logic. Despite this complexity, the optimized recursive DP approach is highly efficient for large inputs. After evaluating all the approaches, the chosen strategy is the recursive solution with memoization. This method strikes a balance between simplicity, efficiency, and scalability. While the iterative DP approach is also a viable option, the recursive solution is easier to implement and avoids storing unnecessary intermediate states. Additionally, it leverages memoization to eliminate redundant computations, ensuring that the algorithm runs with a time complexity of O(n). This approach is scalable to handle large inputs effectively and is straightforward to implement compared to more optimized but complex methods. However, it's important to note that recursive DP can be slightly more prone to stack overflow than iterative DP. Nonetheless, with proper memoization, this drawback is mitigated. In conclusion, the recursive DP approach is a well-rounded and practical solution for this problem, balancing performance and simplicity effectively. To solve the problem of finding the minimum number of days to reduce n oranges to 0, we have three possible operations: eating one orange, dividing by 2 if the number is divisible by 2, and dividing by 3 if the number is divisible by 3. The goal is to determine the smallest number of days required to completely consume all the oranges. The first approach we can consider is a brute force method using recursive simulation. The intuition here is to simulate every possible action at each step and recursively calculate the minimum number of days required. For each value of n, we evaluate all three possible operations and then choose the operation that minimizes the remaining days. The algorithm starts with a base case: if n equals 0, no days are needed, so we return 0. For the recursive case, we compute the minimum number of days required for each of the three actions. For example, eating one orange would result in n1 plus 1 day, and we continue this process recursively. This approach ensures that we explore all possible paths to find the optimal solution. When considering the possible actions, dividing by 2 or by 3 is only valid if the number n is divisible by 2 or 3, respectively. For instance, if n%2 equals 0, we calculate the result as 1 plus the minimum days for n/2. Similarly, dividing by 3 is valid only when n%3 equals 0, and we compute the result as 1 plus n/3. Finally, we return the minimum of these three results, subtracting 1, dividing by 2, or dividing by 3. To optimize this approach, we use memoization. By storing the results of previously computed states in a dictionary, we avoid redundant calculations and significantly improve efficiency. In the provided pseudocode, the recursive function min_days checks if the result for the current state exists in the memo. If it does, we simply return the cached result. Otherwise, we calculate the minimum days for the three actions, store the result in the memo, and return it. This ensures that each state is computed only once. The wrapper function min_number_of_days initializes the memoization dictionary and calls the recursive function. This combination of recursion and memoization allows us to solve the problem efficiently while maintaining correctness. There are several key insights that help us understand why this approach works. First, the problem naturally breaks down into smaller subproblems, making recursion an ideal choice. Each state, whether it's n1, n/2, or n/3, feeds into the next, and solving these smaller states recursively builds up to the final solution. However, without memoization, this recursive approach would repeatedly solve the same subproblems, leading to exponential time complexity. By storing results in a dictionary, we avoid this redundancy and reduce the complexity to polynomial time. It's also important to note that a greedy approach, where we always divide when possible, is not guaranteed to produce the correct result. For example, when n equals 10, subtracting 1 to make the number divisible by 3 leads to a faster solution than dividing by 2. This highlights the importance of exploring all possible operations exhaustively. Additionally, small edge cases, such as n being 1, 2, or 3, must be handled carefully to ensure the algorithm works for all inputs. The use of a memoization table is crucial here, as it provides efficient lookups and inserts. Lastly, the recursive structure relies on the call stack, which is another factor to consider for large inputs. Together, these insights underline the importance of balancing exhaustive search with optimization techniques like memoization. Now, let's analyze the complexity of this approach. The time complexity is O(n), where n is the number of oranges. This is because each state is computed at most once and stored in the memoization table. The space complexity is also O(n), as we need to store the memoization table and account for the recursive call stack. There are some optimizations we can apply to further improve the solution. For example, we can use an iterative, bottom-up dynamic programming approach to avoid stack overflow when working with very large values of n. Another optimization is to pre-compute results for frequently queried values of n. This is especially useful in scenarios where the function is called multiple times with different inputs. To illustrate how the algorithm works, consider the case where n equals 10. We begin by evaluating the three possible options, subtracting 1 to get f(9), dividing by 2 to get f(5), or dividing by 3, which is not valid for n equals 10. We then recursively compute f(9) and f(5). For f(9), we can subtract 1 to get f(8), or divide by 3 to get f(3). For f(5), we can subtract 1 to get f(4), or divide by 2 to get f(2). This recursive process continues until we reach the base case, where f(0) equals 0. At every step, memoization ensures that we don't recompute results for states we've already solved. For instance, once we calculate f(5), we store the result in the memo table, so it can be reused immediately if needed later. This optimization is key to the efficiency of the algorithm. In the example of n equals 10, following this approach results in a minimum of 4 days to reduce all the oranges to 0. This is the optimal solution based on the rules provided. By combining recursion, memoization, and dynamic programming principles, we ensure that the solution is both correct and efficient. The recursive structure guarantees that all possible paths are explored, while memoization avoids redundant computations. Together, these techniques demonstrate how to effectively solve a problem with overlapping subproblems and optimal substructure. This problem serves as a great example of how dynamic programming can transform a seemingly complex problem into a manageable and efficient solution. Here, we start by defining a class called solution and within it, a function mindice that takes the number of oranges, n, as input. To optimize the solution, we introduce a memoization dictionary called memo to store results of subproblems, which helps avoid redundant computations. Inside the DFS function, we first handle the base cases. If there are no oranges left, the result is 0 days since no action is needed. If there's only one orange, it takes exactly 1 day to eat it. Next, we check whether the result for the current number of oranges already exists in our memoization dictionary. If it does, we return the cached result to save computation time. Now, moving to the recursive logic, we consider the first option, eating 1 orange. This takes 1 day, and we recursively solve the problem for oranges 1. This gives us the number of days required if we reduce the count by 1 at a time. Next, we introduce the second option, where we check if the current number of oranges is divisible by 2. If it is, we calculate the days required by dividing the oranges by 2 and adding 1 day for the division step. If not divisible by 2, we set the result for this path to infinity to ensure it doesn't affect our minimum calculation. For the third option, we check if the number of oranges is divisible by 3. If divisible, we calculate the number of days required by dividing the oranges by 3 and adding 1 day for this operation. If it's not divisible by 3, we set the result for this case to infinity. Once we've evaluated all three options, eating 1 orange, dividing by 2, and dividing by 3, we determine the minimum days required among these options using Python's min function. This minimum value is stored in our memoization dictionary for the current number of oranges to ensure we don't recompute it later. Finally, we return this value. At the end of the function, the recursion is initiated by calling DFS with the given number of oranges, n, as the starting point. This approach efficiently calculates the minimum number of days to eat all the oranges using memoization to handle overlapping subproblems. Here, we begin by creating a solution class and importing the necessary utilities. The main method, mindays, takes an integer n, which represents the number of oranges. To optimize our solution, we use a memoization map to store the results of subproblems, ensuring that we don't recompute results for the same number of oranges multiple times. The actual computation is delegated to a recursive helper function called DFS, which we invoke with the initial number of oranges and the memoization map. Inside the DFS function, we first handle the base cases. If there are no oranges left, it will take 0 days to finish. If there's only 1 orange, it takes exactly 1 day to consume it. Next, we check if the result for the current number of oranges is already present in our memoization map. If it is, we simply return the cached result, avoiding redundant calculations. Now, within the DFS function, we calculate the number of days required for 3 potential options. The first option is eating 1 orange, which takes 1 day, and we recursively calculate the days needed for the remaining oranges. The second option is considered if the number of oranges is divisible by 2. Here, we divide the oranges by 2, which also takes 1 day, and then recursively solve for the remaining half. Similarly, the third option applies if the number of oranges is divisible by 3. In this case, we divide by 3, add 1 day, and recursively calculate the result for the remaining oranges. Finally, we determine the minimum days needed among these 3 options, store the result in our memoization map, and return it. This ensures that we are always working with the most efficient solution for any given number of oranges. Here, we're looking at an example where n equals 10. The goal is to calculate the minimum number of days needed to eat all the oranges. To do this, we consider the 3 allowed operations, eating 1 orange, dividing the number of oranges by 2 if divisible, or dividing by 3 if divisible. Starting with DFS 10, we check if this value is already in our memo or if it's a base case, which it isn't. This leads us to explore 3 potential options. First, we could eat 1 orange, which reduces the problem to DFS 9. Second, since 10 is divisible by 2, we divide it by 2, resulting in DFS 5. The third option, dividing by 3, is invalid because 10 is not divisible by 3. Now, focusing on DFS 9, we again explore the 3 options. Eating 1 orange leads to DFS 8, dividing by 2 is not valid since 9 isn't divisible by 2, but dividing by 3 is valid, giving us DFS 3. This process of exploring options continues recursively for each subproblem. When we reach DFS 5, we again analyze the 3 possibilities. Eating 1 orange results in DFS 4. However, dividing by 2 or 3 isn't possible because 5 is not divisible by either. As we resolve these recursive calls, we eventually hit the base cases, DFS 1 equals 1 since it takes 1 day to eat 1 orange, and DFS 0 equals 0, as no oranges are left to eat. Using memoization, we compute intermediate results. For instance, DFS 2 takes 2 days, one to divide by 2 and another to eat the remaining orange. Similarly, DFS 3 also takes 2 days, DFS 4 takes 3 days, and DFS 5 takes 4 days. By building up these results, we calculate that DFS 9 takes 3 days, as it's the minimum of the valid options. Finally, DFS 10 is resolved as 4 days, combining the results of its subproblems. Therefore, the minimum number of days to eat 10 oranges is 4. Now, let's examine a smaller example where n equals 6. Our task remains the same: find the minimum number of days to eat all the oranges. Starting with DFS 6, we again evaluate the 3 options. The first option, eating 1 orange, reduces the problem to DFS 5. For the second option, dividing by 2 is valid since 6 is divisible by 2, resulting in DFS 3. Similarly, dividing by 3 is also valid, leaving us with DFS 2. From our previous computations, we know that DFS 5 takes 4 days, DFS 3 takes 2 days, and DFS 2 also takes 2 days. Combining these, we calculate that DFS 6 is the minimum of 1 plus DFS 5, 1 plus DFS 3, and 1 plus DFS 2, which equals min 5, 3, 3 equals 3. Thus, it takes 3 days to eat 6 oranges. This example highlights how memoization allows us to reuse previously computed results, significantly simplifying our calculations. Finally, let's consider the simplest case, where n equals 1. This is a base case, meaning we already know the result: it takes exactly 1 day to eat 1 orange. Therefore, DFS 1 is directly equal to 1. With this, we can summarize some key insights from this problem. The solution leverages memoization to store results of subproblems, ensuring we don't repeat computations. At each step, we explore the 3 options: eating 1 orange, dividing by 2, and dividing by 3, and select the minimum number of days. Base cases like n equals 0 and n equals 1 serve as the foundation for recursion, guaranteeing that the algorithm terminates. By balancing greedy decisions with recursive exploration, we achieve an optimal solution that minimizes the number of days required to eat all the oranges. To analyze the time complexity of our solution, we start by considering its recursive depth-first search approach combined with memoization. For any given number of oranges, n, the function explores up to 3 possibilities: eating 1 orange, dividing by 2 if divisible, and dividing by 3 if divisible. Without memoization, this could result in many redundant recursive calls. However, memoization ensures that each distinct state of oranges is computed only once. This optimization limits the recursion tree to at most n unique states. The distinct states correspond to the unique values of oranges that can be reached, starting from n. Each operation, whether subtracting 1, dividing by 2, or dividing by 3, reduces the number of oranges, and this ensures that the recursion depth grows logarithmically for division operations and linearly for subtraction. As a result, the total number of states is proportional to n. For every distinct state, up to 3 recursive calls are made, one for subtracting 1, and others for dividing by 2 or 3 if applicable. However, thanks to memoization, the result of each state is computed only once and subsequently retrieved in constant time O1 for all future calls. This means that the overall time complexity is determined by the number of unique states, which is proportional to n. Therefore, the time complexity of the solution is O(n). Now, turning to the space complexity, we need to account for 2 factors: the memoization dictionary and the recursion stack. The memoization dictionary stores the computed results for each distinct state, which in the worst case requires space for all integers between n and 0. This results in a space usage of O(n). The recursion stack contributes additional space usage. If we repeatedly subtract 1 from oranges, the recursion depth can grow linearly with n. In such cases, the stack space usage is also O(n). Combining the 2 factors, the memoization dictionary and the recursion stack, the overall space complexity of the solution is O(n). When comparing this to a brute force approach, the efficiency of the memoized DFS becomes clear. In a naive solution without memoization, we would explore all possible combinations of operations, leading to an exponential time complexity of O(3 to the power of n), as there are 3 recursive branches at each step. Memoization drastically reduces redundant computations, ensuring that each state is calculated only once, which reduces the complexity to O(n). Now, considering the best, average, and worst cases, we see that the solution's time complexity remains O(n) across all scenarios. The best case occurs when n is a power of 2 or 3, allowing maximum division operations and minimizing the recursion depth. On the other hand, the worst case occurs when n is not divisible by 2 or 3 at each step, requiring more recursive calls and resulting in deeper recursion. Even in this worst case, the complexity remains O(n), though with a higher constant factor. In the average case, for random values of n, the recursion depth and the number of states are still proportional to n, leading to an average case complexity of O(n). The mathematical justification for this big O complexity is straightforward. First, memoization ensures that each state is processed only once. Second, the computation for each state involves only a constant amount of work, including up to 3 comparisons and recursive calls. Finally, the total number of distinct states is proportional to n, since the operations consistently reduce the number of oranges. These factors together ensure that both the time and space complexities of the solution are O(n), making the approach efficient and scalable, even for large values of n. When tackling this problem, there are a few common mistakes you should watch out for. First, overcomplicating the base cases in a recursive solution is a frequent pitfall. It's vital to clearly define when the recursion should stop, for example, when the number of oranges is 0 or 1. Failing to handle these base cases properly can lead to infinite recursion or Stack Overflow errors. Another critical mistake is forgetting to memoize results in recursive implementations. Without memoization, you end up recalculating the same subproblems repeatedly, which can significantly increase the time complexity, especially for cases like solving for n divided by 2 multiple times. Additionally, edge cases are often neglected. Small inputs like n equals 1 or 2, as well as very large inputs, such as values greater than 10,000, must be thoroughly tested to ensure your solution is robust. Finally, failing to prioritize operations correctly can lead to suboptimal solutions. For instance, when deciding between subtracting 1, dividing by 2, or dividing by 3, it's important to carefully analyze which operation minimizes the number of steps in each scenario. Another common misconception is assuming that a greedy approach, always applying the largest division operation first, will consistently yield the best result. While this might work in some cases, it's not universally optimal. Sometimes, a strategic combination of operations will lead to fewer steps overall. Now, let's focus on key insights that can help during interviews. This problem is a textbook example of dynamic programming and recursion with memoization. Recognizing the optimal substructure and overlapping subproblems is crucial to solving it efficiently. It's also important to understand the trade-offs between different approaches. For example, a recursive solution without memoization has exponential time complexity, but with memoization, it reduces to O(n). Iterative dynamic programming solutions also achieve O(n) complexity, but you should be able to discuss why memoization is critical in the recursive approach. Be prepared to explain how you handle edge cases, both for small and large inputs, and why your approach is efficient. Lastly, don't forget to ask clarifying questions about constraints, such as the maximum value of n, and whether operations involving floating point numbers are allowed. This problem also shares similarities with several other dynamic programming challenges. For instance, LeetCode 322, the coin change problem, also involves minimizing the number of steps to achieve a target using dynamic programming. Similarly, LeetCode 983, minimum cost for tickets, requires minimizing cost across different choices, which is conceptually related. Another example is LeetCode 931, minimum falling path sum, where the focus is on minimizing a path cost, showcasing the versatility of dynamic programming techniques. While the themes of these problems may differ, they all share patterns of optimal substructure and overlapping subproblems. Even LeetCode 300, longest increasing subsequence, though not directly related, highlights the importance of recognizing these patterns. Familiarizing yourself with these problems can strengthen your understanding of dynamic programming and enhance your ability to spot connections across different challenges. There are also alternative approaches to consider when solving this problem. One option is using iterative dynamic programming. Instead of relying on recursion, you can construct a bottom-up DP table to store results for all states from 0 to n. This eliminates the risk of Stack Overflow and can be easier to debug. However, it may require more memory to maintain the DP table. Another approach is to frame the problem as finding the shortest path in an unweighted graph and solve it using breadth-first search, or BFS. Here, each state, which represents the number of oranges, is treated as a node, and the operations subtracting 1, dividing by 2, or dividing by 3 are the edges. BFS guarantees the shortest path but may demand significant memory to manage the queue. Lastly, a greedy approach could be attempted by always applying the largest division operation first. While this is fast to implement, it's not always accurate, as it can miss scenarios where subtracting 1 initially leads to fewer overall steps. Each method offers trade-offs, so understanding their strengths and limitations is key to selecting the most appropriate one for the given problem. Great job! We've reached the end of this problem walkthrough. We explored strategies to minimize the days required to eat all the oranges, leveraging dynamic programming and greedy techniques. Remember, this problem reinforces the importance of understanding constraints and optimizing recursive solutions. Thanks for joining me today. Be sure to like, subscribe, and stay tuned for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!